This is a help video for the DC Operational Amplifiers game in Circuit Tutor, Level 2, Problem Type 3. So as always, we recommend strongly that you go through the introductory tutorial for this game prior to trying any of the exercises, as that will provide a lot of very important background information about how op-amps work and how we solve these types of circuits. In addition, it would be a very good idea to view some examples at the appropriate level prior to starting to work problems yourself. So for right now, I'm going to go straight into the game. Now we see we have a little bit different type of op-amp circuit, and we do have the help instructions here coming up also, which we can always access from the help button up here on the menu. This one has a single operational amplifier pointing to the right. We notice it does have proper negative feedback from the output through a network of resistors here, including one that goes to ground, back to the negative input terminal. And the input, basically represented by this independent voltage source, is going to the negative input. So we expect that this would basically be an inverting type of amplifier with a negative gain, therefore. However, things are a little bit different because we don't have a simple feedback resistor. Instead, we have this sort of T network where one branch of that goes to ground, which is interesting. And remember that all these different ground symbols, like here and here and here, as well as the ones that are on the power supplies, the positive and negative power supplies for the op-amp, which are not shown explicitly here, but represented indirectly by this little ground symbol, all those grounds are connected together by invisible wires. So this is actually a more complicated circuit than it looks. And remember that inside the op-amp we have a very large input impedance connected between the positive and negative terminals. It's essentially infinite in the ideal case, so there's no current going in here, no current going in here, and then we have a voltage controlled voltage source connected to the output, which basically means that we have an infinite gain here, multiplying the value here minus the value here, the voltage difference of those two voltages, to get the output voltage. And because that gain is infinite, it basically forces through this feedback loop this difference to be zero, essentially, because this has to be a finite voltage in order to avoid saturating the op-amp. So with this in mind, we're going to go ahead and solve this problem. As I said, it's a little bit different topology than you might be used to, but it's still solvable by the same basic methods. So we'll begin by doing a nodal analysis, as always for op-amp circuits, because they may be non-planar and some of the circuitry is kind of hidden inside the op-amp. So we start out, because we have an independent voltage source, we will need a voltage constraint equation. So I'll select that to write that. Again, we're not choosing our ground because that's already fixed by the one that powers the power supplies, and so we really can't choose our ground in this type of circuit. Okay, so our voltage source is basically controlling the voltage of node 1. So that's going to be V1 equals a fixed value of voltage. So I'll just fill that in there as V1. And the voltage is going to be clearly 4 volts because that's the positive side. So basically V1 minus 0 equals 4, or in other words, this formula. So we'll go ahead and check that. That is correct. Then the next type of special equation that we have for op-amp circuits that we don't have for non-op-amp circuits is the op-amp voltage input constraint equation, which basically reflects the fact, as I already said, that the voltage of the two inputs is forced to be the same by virtue of the feedback of the op-amp circuit. And so what that really means is, because this positive voltage is being held at ground, the negative side is also effectively being held at ground, even though it does not have a direct connection or any current flowing to ground. It's kind of an unusual thing, but it's the feedback that causes that to happen. So that equation therefore says that V2, since this input voltage is 1, V2 must also be 0. Again, it's not always 0, it's whatever the other terminal's voltage is, but in this case, as I said, it is 0. So that would say V2 equal to 0. And that is correct. Then we need to go to the sort of central equations in any nodal analysis, which are KCL, or Kirchhoff's current law equations, summing the currents leaving or perhaps entering each node. So we have 4 nodes to consider here, V1, V2, V3, and V4. If we think about V1, however, we realize we cannot write a KCL equation there because it is connected, in fact, to a voltage source that goes to ground. And we don't know the current a priori through a voltage source. It's whatever it needs to be. It's determined by the rest of the circuit. And so without solving the entire circuit, we cannot determine that current easily. And so we won't attempt to write that, and we don't need to because we already have a constraint equation for that node. So how about node 2? Well, again, remember that the input of an op-amp is essentially an open circuit, which means there's no current going in here. And the other two are resistors, so we can indeed write a KCL equation there, and that means that we must do that in order to have enough equations. So I'll select that node. And so we have the current going here between two different nodes and another current going here to V4, again, two different nodes. And that's all the currents there are there because, again, this current is 0. So the current through the 1 ohm will just be V2 minus V1 divided by the 1 ohm. And then the current going from V2 to V4 will be V2 minus V4, the voltage difference that's driving that current, divided by the resistance in that circuit, 6 ohms, using, again, Ohm's law. So we'll now check that equation, and that is correct. So now we'll consider node 3. So I want you to think for a moment if we can write a KCL equation for node 3. So the answer is that no, we cannot write a KCL equation for this node because implicitly, even though it's not shown explicitly, the output of an op-amp is effectively that of a voltage-controlled voltage source, as I mentioned before, and is covered in the introductory tutorial. So because of that, we don't know the current on the output of the op-amp. There is current. It's coming from the power supplies, basically, through the which eventually connect to ground, which is why I show schematically a little ground symbol there, although there isn't really a direct ground connection to an op-amp, but it implicitly has that because of the power supplies, the positive and negative supplies. In any case, we don't know this current, so we can't write a KCL equation here. So then we'll go to node 4, and that one is connected only to resistors, so we definitely can write a KCL equation there and must do so. So we'll select that one. And we have 3 currents here, one going to another node, so that will take this type of term, another one going to node 3, again a difference of node voltages, and finally one going directly to ground, so that involves only a single node voltage. And then the sum of those 3 terms must equal 0. So now through the 6 ohm we have the voltage driving that, which is V4 minus V2 divided by the 6 ohms. And then the current through the 1 ohm is going to be V4 minus the voltage on the other side, which is V3 here, this blue colored node, divided by the resistance there, which is 1 ohm. And finally, the current going down to the 4 ohm is just the V4 minus 0 divided by the 4 ohms. Sorry, by 4 ohms. Okay, so we'll check that. And that is correct. And now we've written enough equations because we have 4 node voltages and we have 1, 2, 3, 4 equations involving those voltages, so that's sufficient to solve. In fact, a couple of the voltages we already know even, so that makes it even easier. And we do, however, have the 2 SOT variables. So we're going to need to write, first of all, a SOT branch current, because I0 is a branch current through a voltage source, so going through a single branch. So I0 will equal something. And if we look at it, you say, uh-oh, that's the current of a voltage source, which we don't know in general. However, in this case, we're lucky because it's in series with a resistor. So we can use the current through that resistor going to the right, which would have to be the same as I0. If there were multiple things connected here, we would have to add currents going in different directions. But fortunately here there's just one, so that makes it very simple. So it's going to be the current going to the right through the 1 ohm will just be the voltage difference driving that, which is V1 minus V2 divided by that 1 ohm. And that'll have to be the same as the current going up through here. So again, the voltage source does not control its own current. It's determined by something else in the circuit, which we're illustrating explicitly here. Okay, then we also need V30, which means V3 minus V0, which is the ground or 0 volts. And so we write an equation for that, which is really a fairly trivial equation. just uses the definition to say it's V3 minus 0, and it's not V0 because that's not even defined here. So we'll just call it V3. Okay, so we'll check that, and that is correct. And now we have all the slot variable equations and the main equations, so we're done writing equations. So we'll click No More Equations. And now it reminds us that we need to put these into a standardized form in order to solve them. So we'll do that on the next form. So now the first equation is very simple. It just says V1 equals 4. So that means a coefficient of 1 for V1 and a constant term of 4. And everything else is left at 0. V2 is equal to 0. So we can put a 1 here, or for that matter, really any value, but 1 will work, is equal to 0. And then the next two equations are less trivial. So we have here, for the V1 term, we just have this term here, which is a minus 1. So we'll put a minus 1 there. Not a 10, but a 1. Get rid of 0. And then for V2, we have a 1 plus a 1/6. So that will be 6/6 plus 1/6 is 7/6 for V2. So I could even write that just as a fraction, 7/6, and it'll automatically convert that to a decimal for me, 1.167, or you could have typed it that way as well. Presumably that may be a familiar decimal to you. V3 is not present, so we leave that at 0, and V4 is just minus 1/6, which again we can enter as minus 1/6, or you could just type the decimal of minus 0.1667, which it'll put in automatically. Okay, and then the last equation, we have no V1 there, so we leave that 0, and V2 is minus 1/6, so again, minus 1/6. V3, here we have just a minus 1, and V4 we have a 1/6 plus 1 plus a quarter, and I just wrote that on paper here, and just using a calculator, that's 1.417, and that completes the equations, so we'll check those, and those are correct. So we have the simplified equations now, standard form, and now we'll just put those into a matrix, although we won't probably really want to use a matrix here to solve. It would be a very inefficient way of doing it, but we'll copy the coefficients there just with that button and check that. So if you were going to use MATLAB or something, you could use that, but again, it's probably not really necessary at all. And in fact, it reminds us it's not a good idea to use MATLAB or a calculator to do this. Rather, we can do it by simple substitution, because that will really be much more efficient if you're just doing hand calculations, as you would do on a test, for example. Hint, hint. Okay, so now we have to put in the values, or if we want to, we could always skip this and just go straight to the answer. That is an option, if you know what the answers are, or if you can figure it out easily. But here I'll just enter them. So V1 is 4 volts. So we'll put in 4 there. V2 is 0, so we'll leave that at 0. And then what we really need is V3 and V4. Those are given by these other equations, which are written here in simplified form. So we'll need to kind of solve those, but they're pretty easy. So this first equation here, that can be written as minus 1 times V1, which V1, remember, is 4 volts, as we found here. So I just put in a 4. Plus the 1.167 V2. Well, V2, remember, is 0, so that just basically that term goes away. And then no V3 term here, but minus 0.1667 V4. So I just put that in, and we have only one unknown in this equation now. So we can easily solve that. Just bring this term over to the right, and then divide by the coefficient. So we're going to have a negative 4 here divided by the what's now a positive 0.1667 after we put that on the right. And negative 4 divided by 1/6, well, that's pretty easy. That's just negative 4 times 6, or negative 24. So we'll put in that value here as negative 24. And likewise, the last equation is also pretty easy. So we have no V1 term. So just the V2 term is a minus 0.1667 times V2, which is 0. So that really just goes away. And then the V3, it's minus V3. and then the plus 1.417 V4. Well, we just found V4, so we can just put that in here as negative 24. And then, once again, just bring the V3 over to the right, and we just have this, which we can work out on a calculator, is negative 34 volts. So I'll put in our V3 value there as negative 34 volts. And now we'll check those answers. They are correct. And now we just need to calculate the SOT quantities using the SOT variable equations that we've already written. So I naught is V1 minus V2 over 1. So that's just 4 minus 0, or just 4 divided by 1. So that's pretty easy. Just do that as 4. And V3, 0, well, that's just V3. And V3 was negative 34. So we could just type that directly. No need for computations. And then we just check those answers. And those are correct. Now it's going to generate a transcript, but I'd also like to just come back and reflect a little bit about this problem, because it's an interesting problem, an unusual topology. And you might say, well, how could we understand this more easily? So first of all, one thing we want to think about is this output voltage really going to be minus 34 volts? What is necessary that's not even shown on the circuit diagram for that to be the output voltage? Let's think about that for a while and see if you can remember the reason, or remember the issue. So the answer is that the output voltage can never exceed the positive and negative voltage supplies. And if your supply voltages are not that large, then you won't get negative 34 volts on the output. In fact, the op amp would be in saturation, and then the assumptions that we made are not going to apply. And that's a different type of situation we'd have to analyze differently. So we have to assume then that we have larger than, say, maybe plus minus 40 volts there would be sufficient, and that would actually require a somewhat high voltage op amp, but such things are available. So just a good thing to keep in mind when you're comparing this to reality, as well as, of course, various non-ideal effects in the op amp, which we have not considered here, which for practical circuit design you probably would want to consider some of those issues, such as finite input impedance and offset currents and things like that. Okay, now the other thing is, how could we understand this circuit more simply? I think that's really worthwhile doing. So if you think about it, it's a lot like an inverting amplifier, except for this extra sort of resistor here, which confuses matters. So how could we account for that? If we think about it, we could use one of the basic ideas that we've learned in circuit analysis. Namely, we've got some sort of source supplying the voltage V3, and then what happens to that? Well, it's being fed back here, and you'd say, well, how could we represent all of this in a way that would make it easier to understand what's going on? And the answer is we could use a Thevenin equivalent circuit, which is a very useful thing in all types of circuit analysis. So in other words, if we think of this as being the voltage V3, that we'd say, let's sort of draw our terminals here and also at ground for the rest of the circuit. So basically we represent this part of the circuit by a voltage source in series with a resistance. Okay? So the first question is, what is that Thevenin equivalent resistance? Well, if we deactivate the voltage source, in other words, connect V3 to ground, then these two resistors are in parallel, and that will be, in fact, the Thevenin equivalent resistance seen from the output terminals, again, from this terminal here and from ground. So 1 in parallel with 4 ohms, that's the product or the sum. So 1 times 4 divided by 1 plus 4 is 4/5 or 8/10 of an ohm. So I've drawn that here as the Thevenin equivalent resistance, 1 ohm in parallel with 4. Then you think about what happens to V3. Well, V3 is not connected to this output directly, so it's not the open circuit voltage, rarely is. Instead, it's really going through a voltage divider. If we imagine this being open circuited, if we just snip this here, we'd get a voltage divider circuit, because remember, V3 comes from ground, is with respect to ground, and comes back to ground here, even though it's not shown explicitly that way. And because of that, we have a voltage divider. And so basically, the voltage comes in, V3 comes in through 1 ohm, goes to 4 ohm, and then this is our output here, or VOC value with respect to ground. So that's going to be the voltage divider formula is the input voltage V3 times the resistor of interest, across which V4 exists. So that's 4 ohms divided by 4 ohms plus 5 ohms. Plus 1, meaning 5. And so that's basically 4/5. And so we get a factor of 0.8 times V3. That's the equivalent voltage source connected to ground to model this circuit. Now this might look a little bit more sensible, because now we can say, well, this voltage here, which is essentially the voltage that's being produced by the amplifier, is going to be the feedback resistance, which is now 6.8 ohms, divided by the input resistance times 1 ohm. And we have a negative sign as well, so it's negative 6.8 basically is the gain, times the input voltage of 4 volts. And so that gives us the voltage at this point, but that is equal to 0.8 V3. So the V3 is really the unknown here. That's the output voltage of the op-amp. And so we can solve this equation then for V3, just dividing by 0.8. And we, in fact, if you do the math there, you do get negative 34 volts, which is what we did through this much more elaborate analysis. But this is a nice way of thinking about it, because it gives us a physically simple picture to understand what's really going on in this circuit, which otherwise is a little bit hard to think about, because it's not just a simple feedback amplifier that we normally have. So anyway, that's just a little extra insight into how this circuit can be thought of in terms of what it's really doing. Okay, so it has created a transcript for us. And okay, you have the option here to view a detailed explanation, so we'll go ahead and do that. Just wanted to re-expand this window here so we can see everything. There we go. And so we have the basically the equations. There's no simplification that can be done. Notice there was nothing in series or parallel. We could not simplify this circuit, unlike some of the other circuits on this level. But we did write the node equations, and it's illustrating that here. And I won't go through all the rest of it, but it does basically explain everything that was done. And you can also get equations, especially for that op-amp input constraint equation, that will give you some explanation of, again, the equivalent circuit model for the op-amp, which looks like that, where ideally R0 is 0, the gain is infinite, and this input resistance is also infinite. Sorry if I said that correctly. R0 is 0. The gain is infinite, and so is this. Anyway, we will go ahead and exit that problem. And again, if you want to review your PDF transcript, the record of your work for studying purposes, you can get that from the Review Work button, which will take you into the appropriate folder. So that concludes this example.